Now let's talk about trends in entropy that are more specific to chemistry examples. For example, entropy increases as a substance goes from the solid to the liquid to the gas phase. And as an example, we have, flipped pages. So if you look at H2O liquid going to H2O gas, and you look up the entropy values from the conversion and equation sheets, you'll see that their entropy under standard state conditions, their units are joules per mole Kelvin, and for liquid water you get 69.9 joules per mole Kelvin, and for gas you get 188.8. So all we're trying to say is that as you go from liquid to gas, the entropy increases, the matter dispersal increases, and if you're asked to draw a picture of that, you would draw a picture of liquid water molecules very close to each other. Oops, that's supposed to be in the container. Very close to each other. You could even draw hydrogen bonds if you want, because there are hydrogen bonds in the liquid phase. And then that's the liquid for the H2O gas. You can draw them very far apart, and we've taken the same molecules and dispersed them, spread them out. Now, as a second example, we can do entropy increases as the moles of gas increase. And here we have an example where we take dinitrogen tetroxide and break it down into 2 moles of NO2. And I'll list them separately here, though we could have easily listed them together. Again, we go to our sheet, we look up the standard entropy values. We would see that dinitrogen tetroxide is 304.3, and each of these is 239.9. Add up the entropy for the products, and it is more than the entropy of the reactants. Entropy has increased. The next trend, entropy increases as dissolved gases leave solution. So the example I want to do here would look at HCl aqueous going to HCl gas. And our picture here is that the HCl aqueous, well, let me give the numbers first. And the numbers don't necessarily mean a whole lot other than when we look at this and see that the HCl gas is 186.9, we see that the entropy has increased, and we see that it has just gone from aqueous to gas, and gases are always the highest entropy phase because they've always got the most matter dispersal. And our picture of this might look like HCl. Right, our pictures are getting more and more detailed. Now we have a covalent bond for our HCl. Actually, that's if it's in aqueous, HCl is a strong acid. It would break up 100%. We would have H+, and it would be surrounded by water molecules in a hydration shell. And the picture gets more complicated from there, but we'll stick with it for hydrogen there. Our chloride. The Cl minus would be closer to the hydrogen portions of the water molecule, since the hydrogen portions are positive. The H plus would be closer to the oxygen portions. Again, this is a very schematic picture, and this picture will get more complicated as you move on, if you do in your study of chemistry. And HCl, of course, in the gas phase, it actually does have a covalent bond, and it is moving. And I'll finish that picture and show it to you on this screen. So there's our HCl flying around. There's our H plus and our Cl minus in solution. And I will say, when I draw it like this, it is a little interesting because you do have the two different parts floating around in solution, and you might wonder which one has more entropy, and it is always the gas phase.